Welcome everyone to our Transport Phenomena project, Inside Out Apple Dehydration, by Nathaly Soliz, Camila Vizuete, and Antonella Reveló.
So let's talk about, first of all, about transport phenomena. So many daily situations reflect transport phenomena without even noticing them. There are three types: momentum, mass, and heat transport. Momentum transport is based mainly in the three physical laws: conservation of mass, conservation of momentum, and conservation of angular momentum. The aim is to determine the velocity profiles by considering the viscosity of the fluids and the geometry of analysis. This can be found, for example, in the analysis of a pipe as well as the wet viscosimeter. An important parameter for this is the Reynolds number, which tells us much information about the studied fluid according to its classification as laminar, turbulent, or transitional flow. Considering the laminar flow, the shear stress depends only on the viscosity and it shows low flow velocities. The Reynolds number for this needs to be less than 2,300. On the other hand, turbulent flow is a function of density and it is mainly found in larger pipes with high flow rates, which are unpredictable. The Reynolds number is greater than 4,000. Finally, transitional flow is a mixture of laminar and turbulent flow, in which turbulence is shown in the center of the pipe, while laminar flow is found near the edges. This depends mainly on frictional energy loss, and the Reynolds number is between 2,300 and 4,000. So as we can see, the Reynolds number is based on the density, the velocity, the dynamic viscosity, and also the characteristic length. So as it was mentioned before, viscosity plays an important role. On Newton's law of viscosity shows the relationship between the shear stress and the velocity gradient. So this is expressed as viscosity and the gradient of velocity. So momentum transport is used for water treatment procedures, as well as the food industry when analyzing different types of fluid, Newtonian and non-Newtonian, in order to get the manufactured product by not affecting its quality and quantity. By using this transport, the analysis allows us to optimize each process by setting up the right conditions that would help predict the results. Now, according to heat transfer, this type of transport works by the principle of conservation of energy, or as it is also known, the first law of thermodynamics. First, it is very important to identify the mechanisms in which energy might be transferred from or to the control volume. After this, energy can be quantified. The object of the study will have two types of energy. The first one is about internal energy, also known as thermal energy, which considers the vibrational, transitional, and rotational motions at a molecular level. Moreover, kinetic energy is considered as well as, and it is related to macroscopic motion of the object of study. There are four types of mechanisms, which are convection, conduction, mechanical energy, and energy transport by subatomic particles, also known as thermal radiation. Convection implies how energy enters or leaves the control volume by analyzing the mass fluxes that are crossing the surface. And in the case of conduction, it is a heat transfer process based on direct contact between the bodies, without exchange of mass. And molecular excitation is left between the molecules of the control volume and the surroundings. It is quantified by the heat flux vector, and the direction occurs along with the temperature changes. In other words, it is proportional to spatial changes in temperature. Just like momentum transport, Fourier's law determines the relationship between these parameters, which is implied by a K and the temperature gradient. So the negative sign shows that heat transfer occurs from high to low temperatures, and in the case of mechanical energy, it is not associated with mass flow. The forces that act on the object of study perform work, and these forces can be of any type, body and surface forces. For this sort of analysis, the force needs to be quantified, and this can be done by considering that once a force acts on the system, a particle will move with certain velocity, and the scalar product between them will result in the work performed by unit time. Now, the last mechanism shows that energy is transferred as a consequence of particles' interaction. The particles might interrelate with matter inside of the object of study, and this will affect the internal energy. For this case, electron or photons transfer will result in this type of energy. According to the transport of electrons, an electric current must flow through the object of study. The collision of these particles will lead to an internal energy rise. This is also known as Joule heating. In the case of transport of photons, materials will absorb photons as they have a wavelength that allows them to perform this. If the material emits photons, a drop in internal energy will be expected, and this last situation is known as thermal radiation, and the most popular way of this is the use of microwave ovens, which are systems with focused radiation. In this way, a temperature profile will be obtained, and during this project, microwave ovens and gas ovens will be compared according to how heat transfer is done, as well as the effects on fruit dehydration. Consider the time and water loss in each of them. Now, the last type of transport phenomena is mass transfer. So mass transfer considers spatial transport of chemical species that interact in a mixture. So the mechanism that govern mass transfer are diffusion and convection. Although chemical reaction might happen during the transfer, it is not considered a mechanism. Nevertheless, it needs to be taken into account for the analysis. Mass transfer happens as a consequence of the interaction between two species with different concentration. The species that diffuses leaves the region of high concentration to a region of low concentration. This type of transfer can be reflected in solids, liquids, and gases. An important equation to define this kind of mechanism is Fick's law. Fick's law states that the diffusion velocity through a membrane is directly proportional to the concentration gradient and inversely proportional to its thickness, just as we can see right above. So now the diffusion coefficient, as it is mentioned there as DAV, corresponds to the diffusion coefficient. So properties such as molecular size, weight, and properties like dipole moment and ionic strength, temperature, and pressure will influence the diffusion coefficient. And it can be determined by estimation, theory, and experiment, just like what we are going to do in this project. So during this project, by setting up a relationship between the concentration gradient and time, the diffusion coefficient will be established. Now, according to convection, there are two types, forced and natural. During forced convection, the fluid motion is produced by an external force. On the other hand, during natural convection, the global motion is developed by changes on the density of the species due to differences in concentration of the medium. Essentially, convection is the combination of advection and diffusion, in which material transfer occurs between a boundary surface and a moving fluid. Nevertheless, there might be the case in which two immiscible moving fluids will interact, in the same way as heat transfer. Quantification of mass transfer can be analyzed by Newton's law of cooling, and the only difference is that instead of temperature variation in mass transfer, the concentration variation is taken into account. Now, in the case of reaction, the principle of mass conservation needs to be applied only to the species in a mixture. So a mass balance will have to be left considering the consumption or generation of the species. Moreover, to quantify this term, it is necessary to use kinetics, and this is reported in terms as RA, which means the net rate of generation in moles per unit time and per unit volume. Now, considering both mechanisms and reaction, a concentration profile will be obtained from this. And mass transfer plays an important role in many chemical procedures that include purification of raw materials as well as separation of products that might imply high cost, and it is also very important to analyze the industrial equipment that will be used for industrial operations that might relate to separation, as the mass velocity transfer will determine the efficiency of the process. That will reflect on the quality. In this project, mass transfer is applied to apple dehydration, in which apple slices will be left in sugar solutions, and then by gas oven and microwave oven heat transfer, the dehydration process will take place. The loss of water during the process will be analyzed as a consequence of water transfer between the apple slices and its surroundings. Now, about the relevance of this project, nowadays it is known that many dehydrated fruits are mainly used as a snack or even as little bags of tea. However, how are dehydrated fruits produced? Essentially, it is all about mass and heat transfer, as we talked about before. The interest arises to continue the study of the kinetics of fruit drying and in order to achieve a rational design of the equipment and optimize the quality of the final product. This can only be done from transport phenomena perspective by considering the different parameters of concentration gradient, time, and diffusion coefficient supported by Fick's law.
So, our general objective is to propose a gas-solid mass transfer model for the dehydration of apples plates throughout homemade techniques such as oven and microwave heat transfer analysis by considering the effect of the different concentrate sugar solutions. Then our specific objectives are: compare different food dehydration techniques in terms of their modeling efficiency and approach to reality. Also, to obtain the diffusivity coefficient of water loss from the apples by obtaining the slope of logarithmic graph based on the model, and then to analyze the effect of different sugar concentrations in apple plates in a dehydration process. The materials used for this project were 15 apples, a gas oven, 10 glasses, 1 scale, 3 knives, 10 spoons, 500 grams of sugar, 1 baking pan, and 1 plate. For the sampling, first of all, the apples were washed. Then, with the help of a knife, the apples were cut in such a way that it facilitated the geometry selected for analysis, which corresponds to plates. The dimensions were 0.5 centimeters of height, 4 centimeters of length, 1.5 centimeters of width. In total, 15 apple slices were cut for analysis. On the other hand, for sugar solution, 5 different concentrations were selected: 0%, 25%, 50%, 75%, and 100%. To start, 5 level glasses were used. 100 milliliters of water were added to each glass. Then for the first glass, sugar was not added as if it's a 0% solution. For the second one, 25 grams of sugar were added. For the third one, 15 grams of sugar, and so on. A different spoon was used for mixing up each of the solutions. It was clear that the 100% concentration had a yellow-like color. If the concentration decreased, so did the color of the solution. After this process, 3 of the apple slices were placed inside of each of the solutions and left for an hour. In this way, the apple will absorb the solution, and this will affect the dehydration process, considering its water loss throughout it. The oven will be preheated at 90 degrees Celsius. Subsequently, the apple slices will be taken away from the solution, and then their mass will be measured. When this is done, all the apple slices will be placed in a baking pan and taken into the oven for about 8 minutes. Then the baking pan will be taken out and left over a surface, so that all the apple slices will adopt room temperature. Later, they are ready to be weighed. This process will be done for a total time of 120 minutes. Now, for the microwave oven dehydration, we place the apple slices on a plate and make sure they were correctly distributed without peeling up and inserted into the microwave. Considering that heat transfer is much faster in a microwave, that time will reduce to a minute for a total of 10 minutes, and repeat the same steps as in the oven. For each of these processes, the humidity will be calculated considering the time of the samples that will be used later to find the diffusion coefficient. Now we will show you a video of the whole preparation process.
PPAP. I have a pen, I have an apple. Apple pen. I have a pen. I have pineapple. Pineapple pen. Apple pen. Pineapple pen. Pen pineapple apple pen. Pen pineapple apple pen. Dance time. I have a pen, I have a pen, long pen. I have an apple, I have pineapple, apple pineapple, long pen, apple pineapple, pen pineapple apple pen. Pen pineapple apple pen. PPAP.
Modeling of the process refers to transient diffusion, in which there is no chemical reaction and the velocity of the process is not considered. As each apple slice is a plate, the rectangular coordinates will be used, considering the x direction. In this case, the water loss will be analyzed, in which the apple plate initially will have a higher concentration of water, and this will be transferred to its surrounding, a region of low concentrations. The aim of this modeling is to find the concentration of water in the apple as a function of position and time. The convective diffusion equation simplifies too, and the initial condition is this. So the first boundary condition corresponds to, at this point, the molar flux x equals 0 is 0, since we have this. The second boundary condition states that the molar flux of water that reach the surface by diffusion should be equal to the molar flux convected to the air. From this, a linear partition is assumed, which leads to, and substituting this last expression into the molar flux analysis, we have this expression when x equals L. In the same way this is done in heat transfer, it will be done for mass transfer. Now it's necessary to simplify the problem by setting dimensionless parameters. First of all, the change in concentration is set as T, and by defining these dimensionless parameters, the diffusion equation corresponds to, and the boundary conditions are adjusted as well. Final equations corresponds to this, and the eigenvalue for this case is lambda tangent lambda equals to beta. And the final equation that reflects this area needs to be analyzed from the mass transfer, and that number and the dimensionless time for theta is beta is higher than 0.01, and this t is higher than 0.1. The first term of the series is enough for analysis and show as follow. So an analogous version stated by Crank in 1956, we have these expressions, and the average of concentration as a function of time is presented like this. So the concentration is proportionally to humidity, so the previous equation can be set as this, where WA infinity is relative humidity and WAO is the initial humidity of the apple plate, and the simplified model is shown next with a logarithm function, and this equation will be used for each concentration analysis so that the diffusion coefficients can be obtained. The data applied to each parameter is WA infinity equals to 10.6 grams, and consecutively the quotient W defined by logarithm of this expression versus time was graphic for each concentration to obtain the diffusion coefficient. So we have here the results, and first for the data for 0% of sugar concentration by oven heat transfer, we have this table and this graphic, and based on the graphic one obtained, it can be observed that cyclically has a linear trend with a relationship value of 0.8275 in an array, which despite not being so close to 1, also does not go so far. This discrepancy is due to possible errors, including the experimental due to external factors, for example, a slight difference in measurement. On the other hand, being a decreasing linear graph, it can be said that the coefficient W is inversely proportional to time, and based on the slope of the graphic, it is possible to obtain the diffusion coefficient. So next we have the data for a 25% of sugar concentration by oven heat transfer. So graphic 2 reflects that the change of water loss as a function of time. The water loss is inversely proportional to time. This means the greater time lapse, less water is lost due to heat transfer. It is clearly that the data obtained from experimentation is very precise due to a strong relationship. We can observe 0.896, and the diffusion coefficient can be obtained from the slope of the equation.
Now for the 50 sugar concentration by oven heat transfer. we've got like a very similar graphic according to the other ones shown by Nathaly. Okay, so we can see that the mass has increased because as the sugar concentration increases, the mass increases as well. So we can see that, and as well the water loss throughout the process. So what can we infer from all of this? So based on this graphic and this table, it can be observed that there is a slightly a linear trend with correlation value of 0.8209, which despite not being so close to 1 and also does not go so far. And this discrepancy is due to possible errors in conducting the experiment due to the external factors, for example, a slight difference in measurements. And on the other hand, being a decreasing linear graph, it can be said that the coefficient W is inversely proportional to time, and based on the slope of the graph, it is possible to obtain the division coefficient as well as on the other graphs. Now for the next case, in which we've got a 75 sugar concentration by oven heat transfer, the situation is very similar, and the mass has increased as well, and also the water loss, as we can all see. In this case, this graphic gives a perspective of the water loss during the experiment, and it is shown that at the greater sugar concentration, the water loss is less than in the other cases with a much lower concentration. Moreover, when setting up the graph, it is clear that by increasing the concentration, there is a resistance from the sugar that changes the graph accuracy due to an R² lower than the other cases. So now for the last case, in which we got like 100% of sugar concentration by oven heat transfer. Just as the other cases and how we described throughout this, the mass has increased as well. And based on the graph obtained, it can be observed that to some extent it has a linear trend with a correlation value of 0.8311, in which despite not being so close to 1, also does not go so far. This discrepancy is due to possible errors in conducting the experiment due to external factors, as we are doing this at home. So also we might experience measurements problems, or maybe with timing, or maybe with the scale for the mass. And also, as the other cases, it can be said that the coefficient W is inversely proportional to time, and based on the slope of the graph, it is possible as well to obtain the diffusion coefficient. Now, for the case of the microwave, we've got some problems with this because the stipulated procedure was carried out, but the expected results were not achieved. The time was reduced to 1 minute for a total of 10 minutes. However, after the second interval, the apples were burned. Then the time was shortened again to 30 seconds and for a total of 5 minutes. But after the fourth interval, the apples were burned as well. So considering that the microwave is old and its power is very high, this dehydration technique could not be carried out. And we wanted to avoid accidents with microwave, so we are just dealing with this with the open heat transfer. So we've been talking about the diffusion coefficient for each of the tables and each graphic. So now we will consider the slope of each graphic in order to calculate the diffusion coefficient of water in apples according to the different concentration of sugar. The final equation gave us which parameters affect the slope, and in this case, M is given by the graphic and L is 0.50 centimeters, which is the height of the apple plate. In this case, we will substitute all of these data in this equation that you can find in the left-hand side. And you can find the table 11 shows the diffusion coefficient for each of the concentration. So we can see that the average diffusion coefficient is equal to 3.40 times 10 to the minus 6. And comparing this to the literature, so the theoretical value, which is 3.55 times 10 to the minus 5, we get the percentage error, and it is 90.4%, which is not very high for doing this at home, but it's pretty high for experimental errors, actually. So now continuing with the convective mass transfer coefficient, we will continue with this, and this is labeled as KC.
To obtain the convective mass transfer coefficient, the model of Kaya et al. 2007 and Roberts 2008 is used because evaporate age conditioning is considered during the dehydration process. A border mass balance was carried out considering M from as constant, and the following equation is obtained. So the method of separation of variables is applied and integrated considering the limits, where T is the humidity contained in the sample at all times, B is the volume of the plate, A is the area of the plate, and T is the time. The mass transfer coefficient is obtained by the following expression, and this coefficient will be calculated at T equals 64 minutes, like it equals 38-40 seconds. So the table 12, we have the convective mass transfer coefficient for apple humidity, and we have the average. We calculate the average convective mass transfer coefficients. So then we calculate the relationship between convective mass transfer and diffusion mass transfer with Sherwood number, with this equation. According to the diffusion coefficient, it is really justifies such a small value as this process is mainly about convention than diffusion itself. Fixed seconds diffusion law was used for mass transfer with the following assumptions: constant diffusion coefficient, transient state, isotropic medium, unidirectional flow. Regarding the transfer of heat, its effect of kinetic was observed with the following assumptions. So infinity plate, surface evaporation, a constant air temperature, the evolution of temperature in the center of the surface. Based on the water diffusion coefficient, the value obtained experimentally had a percent error of 90.4%. Also, this is a very high error under the condition of the experiment. It is not as inappropriate as it would have been expected by performing this very same experiment in the lab. The results might have been more accurate and precise than modeling at home. By obtaining the convective mass transfer coefficient, it is confirmed that the process is based on convection. The diffusion was taken into account for the modeling process, as it will give a much more simplified process that can be determined by using dimensionless parameter as well as a series function. The average convective mass transfer coefficient was 1.37 to elevate to 2 centimeters per second, and this along with the diffusion coefficient supports the obtention for the Sherwood number. So the Sherwood number led to value 2.01 elevate to 7, which according to the equations means that the real mechanism was in fact convention. In other words, all the three values justify the convention mechanism, and that diffusion what really just does is facilitate a much more simplified model that really adjusts on experiment done at home.
As the recommendations were already mentioned by Nathaly, now we're moving forward to the conclusions. Based on the model proposed, it is applied by a transient model which has a dependency of the x-axis. Also regarded is the depth was much smaller than the length. Also, for the development of the model, mathematical methods were applied, such as series resolution, and based on literature, a mass transfer theory obtained on an expression to calculate the coefficient diffusion of water lost from apples to the environment of air. Especially, this expression was obtained by making logarithmic graphs of the humidity difference of apples with the environment and applying Excel. The slope was obtained, which means the diffusion coefficient can be determined. However, based on the recorded data, the final weight of the apple to be completed was shown to increase as the sugar concentration to which the apple was measured increased. This is because the apple absorbed the water with sugar, and as it is known, sugar has the ability to absorb moisture from food, which is why it's, despite exposing it at the same times and temperature of the dehydration, samples of different concentrations, the final weight was higher, as it reflects the moisture absorbed by the sugar, which was not transferred to the air. Finally, it is also concluded that the oven is more efficient in the dehydration process, since even though it requires more time, proper dehydration is achieved. While when compared to the microwave, it was not effective as it depends on its power, and the time to which the apple should be exposed is not known exactly. However, as additional data, it was observed that the higher of sugar concentration the apple has been soaked after exposure to the microwave will be more charged. This is explained because sugar, as it is an organic compound, implies that it contains carbon chains in which, when it is exposed to high temperatures, such as those in the microwave, will then cause to become on edge. Adding to the melting temperature of 186 Celsius degrees, and even though microwave reaches to 100 Celsius degrees, it is common for sugar to reach much more higher temperatures, which contributes to apple being burnt. According to the diffusion coefficient, convective mass transfer coefficient, and Sherwood number, they are all related and they determine the real mechanism of mass transfer. Based on the diffusion coefficient, the value obtained corresponds to 3.40 times 10 to the minus 6 centimeter square per second. By comparing this to the theoretical value of 3.55 times 10 to minus 5 square centimeters per second, the percentage error was 90.4%. Despite that the diffusion coefficient is such a small value, which implies that this mechanism is not governed by diffusion, this is justified because that the convective mass transfer coefficient was also calculated. This corresponds to a much larger value, 1.37 times 10 to 2 centimeters per second. This means that the process is governed by the convective and not diffusion. Moreover, the Sherwood number verifies this as well. In this term, as the Sherwood number is directly proportional to the mass transfer coefficient, it is expected to be very large, considering to the previous result, and actually, the Sherwood number has a value of 2.01 times 10^7, which is a really large value. With this in mind, the modeling process that was built for the apple dehydration is not wrong. The chosen modeling process with the respective assumption was done in order to simplify the calculation, so that the data obtained will be adjusted to it.
Thank you for watching to the end.